Welcome back everyone to this lecture series on actually performing classification of k-nearest neighbors with Python and scikit-learn. In part one of this coding series of lectures, we're going to focus on reading in the data, doing some visualization of the data, and then we'll actually train and build out a model. And the very first model we're going to take a look at is just with k equals to 1. So we're only looking at the nearest neighbor for a single point. Then in part two, we'll actually focus on using something like an elbow method as well as full cross-validation grid search to actually find the best k value. So let's get started with kind of a simple approach, and then in part two, we'll expand on this. I'm going to head over to the notebook now. All right, so here I am at a notebook. I've imported NumPy, Pandas, Matplotlib.pyplot, and then 𝒐𝒵𝑵 as SNS. Let's go ahead and read in our data set. The data set we're going to be working with is called gene expression. So it's underneath the data folder. So if we go back up to the data folder, there should be a file here. You should be able to tab autocomplete this. It's called gene_expression. And if you take a look at this file after reading it in, you'll see that it essentially has two gene expression levels. So an expression level for what we call a gene 1 and an expression level for what we're calling gene 2. And then it indicates whether or not that patient had cancer. So we essentially sequenced the genome of some patient, and then we knew whether or not they had cancer at the time, and then we also measured the expression levels of two genes of theirs. And keep in mind, a gene expression level, and we actually link to this in the lecture notebook, is essentially calculated by the ratio between the target gene we're interested in and one or more reference genes, so essentially kind of household or normal genes, so to speak. So it's just a ratio here of how much you have this target gene versus normal genes. So we can see we have these ratios of gene 1 and gene 2, and then we have cancer present. So let's go ahead and visualize this. A very convenient visualization we can perform is a scatter plot. Since we just have two features, then we could color its hue based off whether or not that patient had cancer. So we can say SNS scatter plot. My data source is the data frame DF, and then for the x-axis we'll say gene 1, and for the y-axis we'll go ahead and say gene 2. Now if you just run it like this, you'll see this scatter plot, but we still don't know which patients had cancer and which patients did not have cancer. So what I want to do is add in my hue parameter to actually color this based off the target label, which is the class, whether or not they had cancer. And so after looking at this, we can see that there's some pretty good separation between class 0 and class 1. What we can't really see, however, is where these classes are kind of overlapping, how many points are stacked on top of each other. So always remember, if you just keep the defaults here, you don't actually know if there's maybe 100 points stacked on top of each other in a certain area. So what we should first do is just check the length of our data frame. And we'll say length of data frame, and essentially reports back that there's 3,000 points. 3,000 points is enough points that we definitely have some points stacked on top of each other here. One good way to fix that is by simply adding in an alpha parameter. So we can say alpha is equal to something like 0.6 or 0.5, and that essentially adds in transparency. So that will give you kind of a better idea visually of how many points you have stacked on top of each other. And recall what we're essentially doing here is when we have a new test point, we want to count the closest number of neighbors to it. And something to keep in mind is you can always hone in on sections in this scatterplot visualization using Matplotlib commands. For example, we can see gene 1 and gene 2 expression levels look like they go from somewhere between 0 and 10 on both axes. If I actually want to explore where they're starting to overlap, I could just use PLT, xlim, and ylim to narrow that range. So I could say, go ahead and focus on a x limit of 2 and 6. So we run that, and now I can begin to see the x limit. And what I could also do is focus on the y limit. So I could also narrow down the y limit I'm looking at to something like, I don't know, let's say between 4 and 8. So I could say focus on between 4 and 8 on the y limit here, and I can begin to see where they're starting to cross over. And of course, you can always change the palette in case you have some trouble distinguishing between blue and orange dots here. You'll also notice some colors that don't look to be either blue or orange, and that's because it's most likely a blue stacked right on top of an orange. Always keep this in mind, especially if you're colorblind. You can always switch out these palettes to kind of help you out. And we can also add in shapes. And you can recall that that's simply the style call. So in the same way we say hue is equal to cancer present, I could also say style is equal to cancer present. And if I run that, that then turns X's and O's here. So then you can really see where things are stacked on top of each other. I can see here what was probably kind of an iffy color. It was actually this orange cross or orange X right on top of a blue circle. So that may help you as well. And then you can also see the whole thing with kind of X's and O's here. And then finally, another plot type you may want to consider, especially since we're dealing with a relatively small data set from a column standpoint, we only have 3 columns, 2 of them are features, is a pair plot. So for this size of a data frame, I'd recommend just doing a pair plot. You can pass in your data source, the data is equal to df, and of course we should color this by hue. So we'll say color this by cancer present, and this will not just show the scatter plots that we just created above, but it's also going to show the distributions of gene 1 and gene 2 to give you an idea of kind of how much information is there. So interesting bimodal distributions on gene 1, and here we can see some clear separations over the kind of normalized distributions of gene 2. Okay, so we have the scatter plots, we have the distributions, and obviously if we had a deeper background in biology, we'd probably want to check out those even closer with other visualizations, possibly maybe doing a histogram or something like that. But that's pretty much all we need to know in order to see that there is some clear separation between the 2 classes. So it's time to actually choose a model to try to make a predictive model that can separate out cancer 0 versus cancer 1 based off these 2 gene expressions. But to begin, we have to prep our data, which means we should be running a train test split as well as scaling our data. We definitely always have to scale our data for k-nearest neighbors due to the fact that it's using distance metrics. So we say from sklearn.modelSelection import train test split, and then we're also going to be scaling our data. So we'll say from pre-processing import standard scaler, run that, and let's set up our x and y. So this should be pretty straightforward. We're going to say x features is equal to the removal of the cancer present column along axis is equal to 1, so it's just gene 1 and gene 2, and then y is equal to that cancer present column. Okay, so we have our x features and our y label. Next step is to split them up, and then we'll perform the scaling. So what we'll do here is we'll say train test split, call the documentation using shift tab, and then scroll down until you find that example, the one we are always using. Copy and paste that. And then what I'm going to do here is I'll just set the test size to 0.3, so keep 30% as our test data set. And then we'll go ahead and say that our random state is just go ahead and keep it at 42, and we'll just run that, essentially keeping very close to the defaults. And now let's scale the data, standard scaler, and we'll create 2 versions. Our scaled X-train data, where we allow the scaler to fit onto the training data, essentially grabbing the min and max value, standard deviation. And then our scaled X-test data, recall we don't fit to that, we merely transform on that. So we'll say transform then the X-test data in order to prevent any data leakage from the test set onto our model. Okay, something else to note here, as I mentioned, when you're dealing with k-nearest neighbors, you always want to scale your data. For this particular data set, it's actually almost already scaled for us. You can see that gene 1 and gene 2 are just going from 0 to 10. There's no huge discrepancy as far as the number ranges for gene 1 and gene 2. So if you forgot to scale this data and still use k-nearest neighbors, you would actually perform probably almost the same as what we're going to do with scaling. However, that's not always the case with real data sets. You're obviously going to have some features with much different ranges than others. So with k-nearest neighbors, because it's using distance metrics in order to actually build out the model, you definitely want to always scale your data. And in general, for many models, there's nothing to be kind of lost from scaling your data, even if it's not necessary. So we have our scaled data ready to go. Now let's actually build out the model. For this, it's really quite simple. We say from sklearn.neighbors, so neighbors is the family of model. We're going to say import k-neighbors, and you'll notice that there's a classifier, regressor, and there's even a transformer. For this section of the course, really, k-nearest neighbors is most effective as a classifier. Obviously, there's going to be situations where you can use it as a regressor or transformer, but we're simply going to classify it as kind of this classification algorithm we're going to learn about. So we have k-neighbors classifier, and as always, I would encourage you to call help on a new model if you haven't never used it, and then check out the parameters. Here we can see the number of neighbors. That's definitely the most important parameter here, and by default, it uses 5. Obviously, we're going to learn about some methods, such as the elbow method that we previously discussed, to try to choose the best number of neighbors. You'll also notice that there's weights, so you can actually weigh certain values, basically say these points are more important than other points, etc. Or you can just use uniform to say all points are weighted equally. And then you can also later on call the algorithm that's actually being used to compute this. In general, I would say just use the default for most of these things because it's probably the most efficient way to use it. The one thing that we do want to take note of is the number of neighbors. That's really something you should be editing and solving for. Everything else, in general, the distant metrics being used, I wouldn't mess around with those unless you have a very specific use case for your data where another distance metric you think would be actually better. But go ahead and use the defaults in general for k-neighbors classifier. The one thing you're going to want to edit is neighbors, but this is something we have to actually discover and test for. So let's do that. We'll start off with essentially the simplest model possible, the k-n model, where our k-neighbors classifier has a number of neighbors equal to 1. And then we're going to take our model and fit it on the scaled X training data against Y train. Run that, and we have our fitted model. So let's go ahead and just quickly see how we could evaluate this model. Just a very simple way would just be with a Y prediction. So say Y predicted values, k-n model predict off-scaled X test. And let's import our classic classification metrics. So that's going to be a confusion matrix and a classification report. And if you want, you can import the plot confusion matrix, ROC curves, etc. But really what we care about here is how accurate we are, as well as our confusion matrix and the classification report. So we'll say, start off with the confusion matrix, just get an idea of performance, comparing Y test versus Y prediction values. And we can see here we're doing all right. It looks like 50 and 47 for a total of 97 points not being classified correctly. And if we can take a look at how many points we actually have in our test set. So we have 900 points in our test set. It looks about like 97 of them are not getting classified correctly. Whether or not that's good performance, again, depends on the actual context of the situation and what previous work has been done. But to get some more details on things like precision and recall, let's go ahead and see print classification report. And we'll say Y test and Y pred. And here we have our classification report. Something to notice here, it looks like precision and recall are doing pretty well. And they're in line with the overall accuracy score we get, which is pretty much exactly what we want. This means we're not really dealing with an imbalanced class set. And in fact, if we say df cancer present value counts and run this, you'll notice we actually have a perfectly balanced class. So 1,500 cancer patients, 1,500 non-cancer patients. So imbalanced classes was never really going to be an issue. And so our precision and recall is performing just fine, and it's very much in line with accuracy. Okay, so this model is actually performing pretty darn good for just taking a look at number of neighbors equal to 1. Now the next question we really need to answer is, what is the ideal k value, the number of neighbors we should be choosing ideally to get good performance? In that case, what we need to do is do something like elbow method or full cross validation. So we'll cover that in the next lecture. I'll see you there.